Welcome back to ch205. So we're going to move on to chapter 3, which is linear algebra and systems of linear equations. So in this chapter, we're going to be talking about how we can solve the system of equations, about matrices, vectors, vector operations, matrix operations, adding matrices, subtracting them, concept of determinant, inverse of a matrix, and so forth. So we're gonna have a quick review on matrix algebra, and then we're gonna move on to spreadsheet calculations. We're gonna install a package which I already put on Blackboard, scripts tab in chapter 3 sections. And then we're going to use that package to do a lot of matrix operations in Excel. Without the package, you cannot do that. All right. So the first concept here is, let's say you have a linear systems of equations. Linear systems means the equations are linearly dependent on the variables. That means if you have like 3 variables in case of equation 3.4, all the variables have power 1, so the power is 1, and we don't have multiplication of variables, like we don't have x1 times x2 or x2 times x3 and so forth. All we have is just x1, x2, and x3. So in all equations, you only see linear term in terms of x1 and x2 and x3. Right. So the main goal of this chapter is if a set of equations like this is given, how we can solve for x1, x2, and x3. Okay. All right. So before doing that, we need to know a little bit about vectors. So vectors, if you remember from your high school algebra, is a list of numbers. We put them like in array or list like this. This is called a column vector because they're sitting in column. You can also have a row vector when I have x1, x2, and x3 all the way to xm sitting in a row. Okay, so that's what we call vector. It has to have only one column. That would be the column vector, and if it has only one row, then it would be called row vector. So like in a spreadsheet, you can easily represent like a column vector, like I can easily put like 1, 4, 5, 7, right? So you can think of this as a vector of 4 by 1, 4 rows, 1 column. I can have a vector like this, 1, 4, 6, and 9. So you can think of these 4 as a row vector for now. Okay, so this is row vector, this is column vector. So let me clear this up. Go back to the notes. So that's about vector definition. An example of it, if you remember from mechanics in high school or maybe from physics. Newton's second law, where force is equal to mass times acceleration. So you can think of acceleration as a column vector. It has 3 elements, the acceleration along the x, along the y, and along the z, and then correspondingly f has also 3 elements, or it could be a column vector with force along the x, along the y, and along the z in 3 elements. Okay, so there you go. So your force is going to have 3 elements in the column fashion: force along the x, force along the y, force along the z. All right. Vector operations. We can add vectors. We can subtract vectors. The only condition here is vectors should have same dimension. If A is a vector and B is also a vector, and A has, let's say, 3 elements in column fashion, B has to have 3 elements in column fashion. If A is a row vector, B has to be a row vector. You cannot add a row vector to a column vector. Okay, so both have to be either column or row as it's indicated in the text. So that would imply element-wise addition. Like if C has like n elements, right? A and B have also n elements, so every element of C would be a summation of the corresponding element of A and B. So the I corresponds to the index of that element, right? Like the second element of C, which is C sub 2, would be equal to A sub 2 plus B sub 2, right? So that means the second element of A plus the second element of B would give second element of C. So that's what I mean by element-wise addition. Okay, so in vector multiplication, in vector addition, you have to have same dimension for both A and B, and then the corresponding C would have the same dimension. All right. So multiplication by a scalar, we can get a vector like A. Imagine A is a column vector. We multiply it by sigma. So then sigma gets multiplied by every element of that vector, right? So, and this is like the element-wise multiplication. I can show you, like, if I have a vector like 1, 2, and 4, and 5 like this, and I want to multiply it by a number like 2. So let's say 2 times, so 2 times this column vector would be equal to, then you have to, you for every element you have to multiply 2 by that specific element. So the first element of the result would be 2 times 1 is 2. The second one would be 2 times 24, it's 48. And then the last one is 2 times 5 is 10. So that's how we multiply a scalar by a vector, which gives rise to another vector with the same dimension of the original vector. Okay, so let's clear this up. All right. Now we can have vector transpose. Vector transpose written by, let's say, if U is a vector, the transpose of it is written by U superscript T. Okay, and what it means is, if I have a vector like 1, 2, 4, and 5, this is a column vector with 4 elements, you get transpose of it. Okay, so if this is, let's say, U, then U transpose, let's call it like this, will be equal to, you read column, you write it as a row. Like this is 1, 2, 4, 5 in column fashion. I write it as 1, 2, 4, and 5. So this is, I read this as a column, write it on a row. Okay, so this is a transpose of the original vector. Okay, so that's what it means by transpose. Linear combination of vectors. If you have two vectors, u and v, same dimension, you can multiply the first one by constant alpha, second one by beta, add them up, you get w. And what it means is, you have to multiply this alpha by every element of u and multiply beta by every element of v, and you do the element-wise addition, like alpha times u1 plus beta times v1 is the first element of w, which is w1. And then alpha times u2 plus beta times v2 gives rise to the second element, which is w2, right? And so forth. So that's what I mean by combination, linear combination of vectors. We have a product of vectors. In that case, we have a dot product or inner product. So by inner product, what we mean by inner product is, if we have two vectors, x and y, first of all, they have to have same dimension. If this is 3 by 1, 3 rows, 1 column, this has to have 3 rows and 1 column. So by inner product or dot product, we put a dot between the two. We have to get the first one transpose and then multiply by the second one. So this is matrix multiplication. Okay? So let's show, let me just carry out one example here. Let's say I have, so here's my x is 1, 3, 5. Oops. 1, 3, 5. And I have another vector, let's say y is equal to, 5, 3, 1. Okay? And I'm going to calculate x transpose. So let's say ws is x transpose times y. Okay? So that means we have to transpose the first one, which means we have to write it in a row fashion, and then multiply by y. So that means 1, 3, 5, this is the first one, right? Times, I just got the transpose of the first one, times the second one in a column fashion is 5, 3, 1. Alright, what is the result? The result is going to be, if you remember from high school, that's a vector multiplication. So we multiply the first element by first element, and then add it to second element, multiply by the second element, plus third element, multiply by the third element. So the result is going to be I'll write it here. The result is going to be 1 times 5 plus 3 times 3 plus 5 times 3. Sorry, 5 times 1. Okay? So 1 times 5, 3 times 3, and 5 times 1. The result is 19. So this is called dot product or inner product. Okay? So, and this is explained in detail here. You have to transpose the first one times the vector, the second vector, or you get the second one transposed, but you have to put it in the you have to write this first and then times the first one, but the first one is not transposed, right? So either x transpose times y or y transpose times x. Either is fine, and that means you get every element of x multiplied by every element of y, and then you add the result for every multiplication. Okay. So here's an example: 1, 2, 3, 2, 1, 2, 3. You want to multiply x by, you want to get the inner product of x by y. So it's 1 times 2 plus 2 times 1 plus 3 times 3, and that's what it's in here. Okay. Vector norm. So norm is a metric, or is a metric indicating the size, sort of the size or magnitude of a vector. And by norm of a vector, we mean if you have a vector with vi elements, we have to get every element, well, we have to transpose the vector and then multiply by itself. You get the result, then you get the square root of it. Okay? So let's go back here in our example. Let's say I have x and I want to get the norm of x. Then what we have to do is the following. So I have to get the square root of it, which means sqrt of the first element of x times itself, so 1 times 1 plus 3 times 3, the second element times the second one, plus 5 times 5. Alright? And then we get the square root of it. So that's the norm of x vector. Okay, that's right here. 1 times 1, 3 times 3, 5 times 5, you add them up, you get a square root of it. Okay. We have orthogonal vectors definition. Orthogonal vectors means the transpose of the first times the second, you get 0. Geometrically means the angle between them is 90 degrees. I mean, this vector is perpendicular to the other vector. So u is perpendicular to v. Now, mathematically, that is proven by just showing if u transpose times v is 0, the dot product of u times v, which is u transpose times v, right? And that is 0. So if you remember from high school, again, we can get the angle between two vectors, and the angle between two vectors is you get a transpose of the first times the second, and then divide by norm of each. By the way, this double vertical lines means norm, according to equation 3.14. Excuse me. All right, so that's the orthogonal vectors. We have orthonormal vectors, which is very close to orthogonal vectors. In orthonormal vectors, we have vectors like u such that u transpose times u is 1. Okay, so this is called orthonormal. If a vector is orthonormal, means the vector times the transpose of vector times itself is 1. Okay, it's the unit vector. Okay, and to do that, we can actually orthonormalize any vector. If you have a u vector, you want to orthonormalize it. You have to divide every element of u by the norm of u. Okay, so if you remember, norm of u is u transpose u, or you go back here. So that's the definition of norm. You divide every element of u by the norm of it. Now this u hat will be orthonormalized, which means if you get u hat transpose times u hat, you get 1. Okay. All right. So I hope this introduced you to some preliminary information on matrix algebra. So thanks for watching, and stay tuned for the next video on matrix operation and using matrix package in Excel.